Here's another piece of apparatus for investigating secondary flow. It is an open channel with a bend in it. The entering flow is about as clean as we could make it. Laminar, uniform velocity, and where we're going to observe it first, that is well clear of the sides and bottom, nearly frictionless. Here's a sheet of bubbles from a vertical wire. We have tried to keep the size of the bubbles uniform and large enough to be seen clearly, yet small enough so that their buoyancy does not spoil their usefulness as fluid markers. Let's see what happens when this flow enters the bend. Here's the radial view. And the top view. And now a tangential view, looking in this way. The streamlines are alike from top to bottom. We can think of this as a primary flow with no secondary flow at all. And we shall use this simple flow as our concept of primary flow in this channel. How about this sheet of bubbles? Although it may appear warped, this sheet is really in one plane, as a top view clearly shows. We might expect the same streamlines as before when we look at it in the bend. Here's the top view. And the tangential view. The streamlines are no longer identical. Thus there is a departure from the primary flow, which we can call secondary flow. How does it come about? Clearly, the entering flow now has a velocity gradient in it. This time, the velocity gradient is not embedded in a boundary layer. In fact, it doesn't matter how the velocity gradient originated. The crux of the matter is that although all fluid particles are moving in the same direction, some are moving more slowly than others, and all are subject to nearly the same pressure forces. When the streamlines are straight, all particles move in the same direction. Where the primary flow streamlines are curved, the pressure forces carry the slower moving particles toward the center of curvature. When the streamlines are curved and there is a velocity gradient normal to the plane of curvature, we may look for a secondary flow. Here's an extreme case. This time, the velocity gradient occupies the entire flow. So it's not surprising to find secondary flow everywhere in the bend. In a situation like this, it is often easier to explain what's going on in terms of vorticity, rather than trying to identify a main flow from which a pressure field could arise. You will remember that vorticity is twice the average rate of rotation of a fluid particle. If we look for vorticity in the straight channel, we see no evidence of it in the streamwise direction. and in the top view we see no evidence of vertical vorticity. But if we look horizontally across the flow, we see that there is vorticity, and it is horizontal and normal to the streamlines. In this case, the vorticity is nearly uniform throughout the flow. We can represent the axis of this vorticity by a fluid line which can be observed from above. We can call this line a vortex line. Helmholtz has pointed out that in a frictionless flow, a fluid line coincident with the vortex line will remain so. That is, the vortex lines are transported by the fluid. Let us assume that our flows are essentially frictionless. Thus, here in the straight flow, one arm of the fluid cross coincides with a streamline, the other with a vortex line. As the flow enters the bend, the streamline leg of the cross begins to turn clockwise. Since the vertical component of vorticity is 0, the other leg must begin to rotate counterclockwise at the same rate. But this other leg represents the vorticity in the flow. This means that as the flow goes around the bend, a component of vorticity appears in the streamwise direction. This component increases as the fluid traverses the turn. In the straight channel, the vorticity represented by this fluid line, you remember, appeared in the horizontal view as a counterclockwise rotation of the fluid. We can watch a vortex line enter the bend and observe the same counterclockwise rotation of the fluid showing up as streamwise vorticity. By looking at the vorticity, it becomes clear why the secondary flow sweeps outward at the top and inward at the bottom in this fashion.